All right, so last lecture, we started moving into the full set of orbitals that we're going to be using to do silicon. The S, px, py, pz orbitals. We looked at their various bonding configurations, the sigma and pi bonds, and then finally, in terms of these YLMs, which is the way they're always spherical harmonics, we showed the relationship between the spherical harmonics and the basis that we're actually going to use, px, py, and pz. And one is just a linear combination of the other. So pz is the simplest one because pz is just directly the spherical harmonic y10. And px is this linear combination of, and py is another linear combination. And the form of the functions are given by this. And so, as you go away from the core of the atom, they're dying off as 1 over r, just as a function of distance away from the center, but they have the symmetry of either x, y, or z. Right? They have the symmetry and the sign of x, y, or z, and that's why they're called px, py, and pz. And if you draw them, they're oriented along the x, y, and z axes. So if we draw, say, px, and once you choose your axes, that chooses the sign of the lobes. So it's going to be positive where x is positive and negative where x is negative. And the same thing for py. It's just going to be oriented along the y-axis. Same thing. Positive where y is positive and negative where y is negative. And just decaying is 1 over r as you move away from the core. But there's that exponential r dependence, right? This is just the angular dependence. There's also that other radial dependence, which we're not even concerned about, which is exponential decay, which dominates the radial dependence. We're only concerned right now about the angular dependence, because that's going to determine the sign of our matrix elements. So we have to understand this to get the sign of the matrix elements correct. The magnitude is just determined empirically to give you the best fit to the known band structure, effective masses, and gaps. But we need to understand this to get the sign of our matrix elements correct, and that is critical. Okay, so now that we know our basis set that we're going to be using, we need to talk about how we're going to calculate the matrix elements for silicon or gallium arsenide or any of these zinc-blende or diamond crystal structures. So there's going to be 4 non-zero matrix elements, and we'll just write them down to define our notation. So 1 is our SS bond, and I'm going to write down, so we've got 2 s orbitals on our A and B atom, and so SA, H, SB. And so these 2 atoms, everything's going to be in a nearest neighbor model. And so these 2 atoms would be, say, the 2 atoms in your unit cell, in your primitive cell for silicon, right? Each lattice site has 2 atoms associated with it. And that's defined as VSS sigma, sort of following what we talked about last time. It's a sigma type bond, and it's between 2 s orbitals. And this is just a notation that goes back to the 50s. And this is going to be less than 0 for the same reasons that we've talked about from day 1. Right? Because the potential is negative, the orbitals are positive, the integral gives you something less than 0, just like our t's. So that's 1 for first one. 2 will be a matrix element between, and this is going to, again, just like we talked about last time, the sign of this is going to depend on how you position it. So if my A atom is here and my B atom is here, this is all positive. And the way I've positioned the two atoms, this is going to be greater than 0. What do we got next? Number 3 is our sigma bond for 2 p orbitals, b, p, p, sigma. And again, because you've got a positive lobe facing a negative lobe, that also is going to be greater than 0.
Does changing it from changing the positions, if you flipped SA and PZB from the
yeah, if you put S on the B atom and
well, if you flip it from, what's it called, the conjugated one, what's it called, the first one, which is the conjugated one, and you put that one where it's not conjugated, what's it called? It's called the
Hermitian conjugate? No. So what are you worried about if I write down this? PZB?
Yeah,
I mean,
yeah,
this,
yeah, exactly. Is that different or is that the same?
this is a real number, so it's got to be the same thing. We know it's a complex conjugate, but that's a real number, so it's got to be the same thing.
Okay.
It's still the p orbital's on the B atom, and the s orbital's on the s atom. It's only if I put the s orbital on the B atom and the p orbital on the A atom, then it's the sign is going to flip. Right? If I now do this, because I'm going to have plus, minus, plus, so the two plus orbitals are facing each other, then that sign, that'll be negative. If I put the p orbital on the A atom and the s orbital on the B atom, right, then the sign will change. So this would give me a negative, this would be a negative VSP sigma. Right, and over here on number 3, either way you do it, it's going to be the same thing. You've got a positive orbital facing, a positive lobe facing a negative lobe. So that will always be greater than 0. And the last one, of course, is the pi bond, equal to V, P, P, pi. So again, this would be my 2 atoms, A, B. This is my Z direction. And this is going to be, what's the sign of this guy? Greater than or less than 0. I heard a greater. We can vote. How many believe it's greater? How many believe it's less? The less have it by 2 to 0. I guess a lot of people abstain. How many abstain? It's less? I heard a very determined less there. Yeah, it is less than 0 because the positive lobes line up, the negative lobes line up. So that, the multiplication of the two wave functions is going to give you something positive, and the potential is negative. So that is less than 0. When we do the overlap integral, the only dependence on that polar angle, if you go back and look at the YLMs, they had like a sine or cosine of theta, and then an e to the plus or minus im phi. Right? So the only dependence on that polar angle phi is that exponential term. And so when you do the overlap integral, you and Cardona call it an overlap integral for these integrals that we're doing here. But if you look at the integral, you're going to have, it's going to be proportional to the angular part over phi, d phi 0 to 2 pi, d phi e to the I phi times m prime minus m. And where m and m prime would be, if you go back to your YLMs, right, it's YLM. L is 1, m can be -1, 0, or 1 for the p orbitals, and m is 0 for the s orbitals, right? So this integral is simply delta, this is a Kronecker delta m prime m. So it means that all these, and this is, m is also the z component of your angular momentum. So what it's saying is that in all these matrix elements, the z component, that you only get matrix elements between orbitals that have the same z component of the angular momentum. Okay, so if we go back and look at our matrix elements here, for these guys, m equals 1 and m equals 1. Same with these guys. And if we back up, what have we got here? For the z ones, those are y1, 0. Remember the pz was y1, 0, so this is m equals 0. And same with s, m equals 0 too. So these are all m equals 0 and m equals 0. So this is why this is sort of another reason why you get these 4 non-zero matrix elements from this basis set that we're going to be using. The 1s and 3p orbitals. Okay, so those are the all the matrix elements we're going to be writing down when we do silicon are in terms of these things that we've just defined here. That's it. And the rest is going to be, and these are a magnitude, and that magnitude is determined empirically to give you the best fit to the actual band structure, as I said, like band gaps and effective masses. And we then are going to be dealing with the angular dependence and the k dependence when we construct this Hamiltonian as a function of k. Okay, so on to calculating the Hamiltonian matrix elements for our crystal, which will be either silicon or gallium arsenide, diamond or zinc blende. So the first thing you do is you define your coordinate system, because this is going to define all the signs of your orbitals. We're dealing with cubic crystals, so we're going to choose our x, y, and z axes to line up with the crystallographic directions 100, 010, and 001. And since it's a cubic crystal, this is pretty straightforward and obvious, right? Like silicon, you choose your coordinate system to line up with the crystal axes. And once you've defined your coordinate system, that defines the direction of all your p orbitals. So this defines your basis states on each atom, which is going to be our s. So each atom is going to have these 3 orbitals. And for future, I may start, just to warn you ahead of time, at some point you realize there's no reason to keep writing px, py, and pz. And at some point I'm just going to start writing x, y, and z for my p orbitals. And we'll keep s as s. If I start doing it without sort of think subconsciously, I'm going to switch into that at some point. Because since there's two atoms in our primitive cell, the A and the B atom, I'm going to have to start differentiating and call it like X sub A and X sub B, and it's easier to write in PXA and PXB, etc. And now we need to start, since it's a nearest neighbor model, we need to consider matrix elements between 2 atoms that form the primitive cell in silicon. Okay, so these 2 atoms are located, the A atom we're going to put at the origin, and the B atom is offset by quarter times the lattice constant A. And in silicon, A is your 5.4 angstroms. So the A is just the side of your cubic unit cell in silicon. So this is A. Okay, the side of your cubic unit cell. This is not the primitive cell. This is the cubic unit cell. And does anyone know how many atoms are in the cubic unit cell of silicon? I have to think about it for a moment myself. There's one atom on each face, right? But that's shared by two cells, so there's 6 faces, so there's 3 face atoms. There's one on each corner, but each corner is shared by 8, you say?
Yeah.
I'll take your word for it. So there's 8 atoms, but each one is shared by 8 cells, so that's 1 for the corner. And then, do you know how many are on the interior of that? There's 4 on the interior. So in this cubic unit cell, there's 8 atoms, but in the primitive cell, the smallest repeat unit, there's only 2. But the repeat unit is not cubic. It's some weird polyhedron type shape. So people prefer to work with something cubic, so you extend it out a little bit until you have something cubic. So A is this typical lattice constant that you find in your textbooks for the cubic unit edge of the silicon unit cell. All right, now if we look at, these 2 atoms, the A and the B atom, well, you've got one at the origin, you've got one offset, so this guy's offset a quarter away along the diagonal of the cube, right? This is 1/4 along the diagonal of the cube. If you can picture that, if you have good 3-dimensional visualization. So if you take the diagonal of the cube from far corner to far corner, this would be your origin. So you've got one atom here and you got the other atom offset a quarter away along that diagonal. So the other atom would be sitting here about a quarter away along that diagonal, right? A vector we're going to become very familiar with, D, is going to be the vector that connects the 2 atoms. So it's the vector that goes from the A atom to the B atom, which is trivial at the moment because the A atom is at 0. The A atom to the B atom. And well, in this case, it's equal to A over 4 times 1, 1, 1. And if you notice, that's not equal to Z hat, right? So all the matrix elements we looked at, we aligned the 2 atoms right along the Z-axis, which made life simple. Now they're not aligned along the Z-axis, so we have to figure out how to calculate these matrix elements when one atom is offset from the other. Okay, so let's, as always, we look at the easy one, which should be SAH. SB. And so we've got one at the origin and one that's out a quarter of the way from here to the far corner of my cube, which would be here, so it should be sitting somewhere here, and you've got this vector that connects the 2 atoms. Sorry, it's the best I can do. Your D vector that connects the 2 atoms. Okay, but s orbitals are spherical. They don't care. Any matrix element between them is only a function of the distance between the 2 orbitals. There's no sign involved. So this is just still equal to our VSS sigma. And so if you look up in tables, you can find these values for silicon and all the common semiconductors. For these parameters to construct the Hamiltonian. Okay, that's easy because there's no sort of angular dependence for an s orbital. Okay, 2, we need put an s on the A atom at the origin and put a py on the B atom, offset by this A over 4, 1, 1, 1. And that's a little trickier. So now we've got, our A atom with an s orbital and our P offset like Py is going to be along the y-axis, offset along this D vector, which is our A over 4, 1, basically the 1, 1, 1 direction. Right? And so we need to figure out what that matrix element is. So this is A at the origin, this is our B. And the way you do that is you sort of like decomposing a vector into its parallel and perpendicular components. These p orbitals transform like vectors, and you can work with them in the same way. And so we're going to transform this into the p orbital into a component that is aligned along the d vector and a component that's perpendicular to the d vector. And that's going to give us a sigma bond and a pi bond. And we already know that VSP pi bond is 0, so the only thing that's going to come out of this is a sigma bond. So when we do this transformation, so I'm going to take this, and the s orbital just stays the s orbital. Here's my d vector, and I'm going to write, I need to decompose this p orbital into a component along the d vector and a component perpendicular to the d vector. And this is going to give me a VSP sigma, and times the cosine of, talk about that, cosine of an angle, plus VSP pi times the sine of an angle. But we know that this is equal to identically 0, so we don't get anything from that thing. We already talked about why that VSP pi is 0. It's due to symmetry. And if I do that, there's a line of symmetry where this is the p orbital is odd, s orbital is even. If I do the integral over all space, I get 0. So then we only have to worry about the VSP sigma component, and so let's talk about that. So what is beta? Beta is the angle between the y-axis and d. So I'm just projecting this as a dot product. If I think of this thing as, y, something along y hat, and I want to know the component along d, I just take the dot product. So beta between the y-axis and d. So it's the angle between the y-axis and d is what beta is. And so just dotting the dot product, which would project this p orbital onto d, would give me this cosine beta term. And we're going to be using these direction cosines a lot, so it's something you probably haven't thought about for a while. So the direction cosines of this d vector are going to pop up all over the place, because we're going to be projecting our p orbitals like parallel to d and perpendicular to d. D is a vector. I guess what I really will be talking about is just d hat, the unit vector in the d direction. Right, the unit vector in the d direction. So L is just equal to d hat dot x hat, which is cosine alpha. M is d hat dot y hat, which is cosine beta. And LMN is d hat dot z hat, which is cosine alpha beta gamma. These are the 3 direction cosines. So just means that d hat is, cosine alpha x hat plus cosine beta y hat plus cosine gamma z hat. Right? That's d hat. It's like any vector you could write like that. And if we remember what, for us, well, we know what d is. So d hat is equal to 1 over root 3, 1, 1, 1, right? Because d was in the 1, 1, 1 direction. So d hat is just the unit vector in that direction. And so for ideal silicon, germanium, gallium arsenide, any of those, all of these are the same thing, and they're just 1 over root 3, 1 over root 3, and 1 over root 3, etc. So for any of the diamond or zinc blende lattices. And I say ideal because, if they're strained, if you compress, squash your crystal, or stretch it, then it's no longer going to have the cubic symmetry and it may change a little bit. But for the ideal unstrained cubic crystal, L, M, and N are going to be the same. But you could imagine, really compressing it so the Z, you're squishing down the Z direction and stretching out the X and Y, and then things would change a bit. And so, with that, we have that if we do one of these, one p orbital, like this, so basically we're just taking the component of that p orbital along the d direction, which gives us the, and the p orbital is along y, so we're just taking basically, d hat dot y hat, which is that cosine beta, which is our m. So we can immediately write down that SA H X B is equal to L V S P sigma. And this is kind of trivial because L, M, and N are all the same for the ideal crystal, and they would only differ if you strain the crystal. And which, for ideal, unstrained is just your 1 over root 3. Now, we need to look at two p orbitals, one on the A atom and one on the B atom. So let's look at that. I've got a p orbital sitting here at the origin, plus minus on the A atom, and I've got a p orbital offset by my d vector, and they're both py, so this will also be oriented along the y-axis, so I'll have something that looks like that. And I've got to decompose that guy into, my sigma and pi bonds. So if I just draw, that's supposed to be a line along the d hat direction. Okay, I'm going to have the components that are aligned along that direction, giving me a sigma bond, plus the components that are perpendicular to that direction that give me a pi bond. And since I'm projecting now two identical orbitals onto the d axis, then I'm just going to get a cosine squared for the sigma bond. So YA H YB is going to equal m squared, which is cosine squared beta, which is the angle of d with the y-axis, right? Projecting this guy onto the d vector. It's just the dot product, which gives me a cosine beta of d with the y-axis. M squared VPP sigma plus, and now, well, I'm decomposing this vector, and so I'm going to have, a cosine squared. The other thing is, so and the two pieces have to add up to 1. So the other piece has to be a sine squared, which I don't know offhand, so I write that as 1 minus cosine squared. So that's 1 minus m squared, right? 1 minus cosine squared, VPP. Right, the two components have to add up to 1. So this is my 1 minus cosine squared, which is sine squared. Okay, and so then by symmetry, if you have that, then the other ones you just get by replacing m with L and n. So just to write them all down, we've got XA, H, XB is L squared, B, P, P, sigma, plus 1 minus L squared. Again, since L, M, and N are the same for an ideal crystal, it's trivial, but they don't need to be the same. Okay, so that's those two kinds of matrix elements. And there's one last one that is really tricky to derive. So I'm going to first just write down the solution, and I just may skip the derivation. And if you really want to see it, you can look in those photocopied notes. I don't know how worthwhile it is to go through that. It's probably not worthwhile. Something that I had to derive myself one point, but let me just write down the answer. So the other one, number 4, is when you have X, A, H, basically just two different type of p orbitals. Y, B. Could be XZ or YZ, just two different type of orbitals on the two different atoms. And so now we're looking at, so I've got a X orbital down here at the origin, aligned along the X axis, so plus, minus. And on the B atom, what have I got? A Y orbital up here, plus, minus on the B atom. And remember that, and of course, the D vector, which is always the same with D hat, is L X hat plus LM Y hat, LM N Z hat, as always for any vector. Those are your direction cosines. And so this matrix element is equal to Lm V P P sigma minus Lm V P P pi. And if I want, once you write that down, as usual, you can immediately write down the other ones, such as Y, A, H, Z, B. And you just, replace these direction, the L and the M, with now the M and the N. So I'll have M, N, and I can just factor it out. V, P, P, sigma minus V, P, P, pi. And similarly, if I put an X and a Z, X, A, H, no, X and, what did I do? I did a Y and a Z, X and a Z. So instead of the M, now for X, I'll have a L and an N, Ln, Vp, P, sigma minus Vp, P, pi. So these are, I think, all the matrix elements we're going to need to construct the Hamiltonian. And if you look at the way we did this, we did it in a very general way. So we did it in terms of these direction cosines of the vector that points from the A atom to the B atom. Now we're going to have, each atom has 4 nearest neighbors. So that A atom has 4 nearest neighbors. We did it for one of them. But we did it in a very general way in terms of these LM and Ns that correspond to the D vector. So each of the neighbors will have a different D vector, all the same magnitude, but just a different direction. And as soon as we know the direction cosines of the new D vector, we just replace these L, M, and Ns with the new L, M, and Ns, and all they're going to do is change sign when you think of this, the arrangement of the atoms. So you'll have the A atom at the origin, the B atom at, in this case, 1, 1, 1. You'll have another B atom at, oh well, we'll see in a minute, it'd be like 1, negative 1, 1. So the sign of these L, M, and Ns is going to be changing, and that's the only thing that's going to differ as we sum up the matrix elements of the 4 nearest neighbors. Okay, actually deriving the VPP sigma component is pretty easy. I'll derive half of this, and you can send you to the notes for the other half of this. The VPP pi is not so easy. So I'm going to derive at least the the sigma part, and then say see the notes for the rest. Okay, so I'm going to derive for this matrix element X on the A atom and Z on the B atom. And so if I draw that, this is X, here's Z. I've got my X orbital down here, and along my D hat direction here, I've got a Z orbital. Again, we're going to treat these states as, the Px is like an X vector and Pz is a Z vector. And what I want to do is decompose, well, I guess to get the sigma part is really, I guess, pretty straightforward. I'm just going to take the cosine of this guy with the D vector and the cosine of this, so I guess I should just get, for the VPP sigma component, I guess I just get, LM N for this guy, and taking the dot product of this, L for this guy, and that just gives me my L, N, V, P, P, sigma. Dotting those into the D vector. It's like X dot D, which is L, and X hat dot D hat, and Z hat dot D hat. So that's the cosine alpha and cosine gamma, which is L and N, which is exactly right what we wrote down. Now the other part is a little tricky, and that's, I'll say, just see the notes. Okay, but this is the final form of all the matrix elements we need. For a complete list of matrix elements, including d orbitals, I may be up there on iLearn, I can't recall. 15-2 of Harrison. One of the books listed in the syllabus, and the table may be uploaded, but this is actually a reproduction of the original table by Slater and Koster, and that original paper from like the 50s is uploaded on iLearn. So anyone in this business knows immediately what you're talking about when you mention the Slater Koster tables. They were the first one to catalog all this values for all these, like VPP sigma, VPP pi, and ditto for the d orbitals, and they also give the form of the matrix element, like what we've been writing down here. So this kind of expression for the matrix elements in terms of the direction cosines. And they also do that for the d orbitals, which are more complicated because they transform like tensors, so it's not quite so easy to derive those. Okay, and so with that, how are we doing? Usually when I say how are we doing, We're not doing well. Okay, well, we're just still doing okay. With those matrix elements in hand, we can now go about calculating the band structure of silicon, which is what we are now going to proceed to do. So, well, we've got 2 atoms in our repeat unit. We've got 4 orbitals on each atom. And we're going to construct block sums for each one of these orbitals. So our block sum basis, we're going to have 8 orbitals, and our k-dependent Hamiltonian will now be 8 by 8. Right? We're going to construct an 8 by 8 Hamiltonian, k-dependent, and then if you send that off to MATLAB, for each k, you construct it, you send it off to MATLAB, you'll get 8 energies for each k. And you plot them as a function of k, and you will construct this E versus k diagram with 8 bands in this model. We're not going to do all that, but we'll look at what they call the high symmetry points. So everything we're doing is applicable to these group 4 semiconductors, or the 3 5s, which have this diamond or zinc blende lattice. We've got 2 atoms in our primitive cell, and we're placing them at 0, 0, 0. And A over 4, 1, 1, 1. So we've got our A atom and we're calling it A and B. Sometimes I may call it A and C for anion and cation. So I'll say, I may slip. This could be a B atom or a C atom, depending on my mood that day. All right, so for gallium arsenide, that would be your anion and your cation, your gallium and your arsenic. And for silicon, they're just 2 silicon atoms. Okay, so those are our 2 atoms. We know the basis. We're going to put an S and 3 Ps on each one of those atoms. I guess the other thing we need to know is, what are the primitive lattice vectors, which define the periodicity of the crystal. So these 3 vectors, if I take these 2 atoms in my basis, and I translate them by any integer multiple of these 3 vectors, I create the entire crystal. And so these are for your F, face-centered cubic structure. You've got A1 is equal to 0, A over 2. Notice these are not orthogonal vectors. These are not orthonormal, they're not orthogonal. And if you draw that cubic, remember we said there's 1 atom on each face. And so there's one on each corner. So if this is my 0, 0, 0, then these guys are pointing to the 3, this would be like A1, to the 3 face atoms. So there'd be one pointing to the face atom here, and there's one pointing to the face atom underneath, and I'm not a good enough artist to draw that. So these 3 A vectors are pointing to the 3 nearest face atoms on the base and on the 2 sides. And they define the periodicity of the lattice. So a generic lattice vector, which you will always write as uppercase R, is just some integer sum of these lattice vectors. So if I translate by any vector like that, and these m's are integers, so then everything is going to look the same. So if I'm sitting at some position and I translate by one of these uppercase R vectors and look around, and it'll look exactly the same. It's periodic in terms of any integer combination of these primitive lattice vectors. And so the entire crystal is just created by translating, taking your 2 atom basis and translating by all possible integer combinations of these lattice vectors. And so when we're going to be writing down things like sum over R, so that's a sum over all endpoints in our Bravais lattice. And of course, n is something that goes to infinity, but it's sort of our bookkeeping n, which normalizes things. So before in 1D we were able to just write a sum over n, where n was our unit cell. And now this is just the same thing in 3D. In 3D, that just becomes a sum over r. Or again, that's the sum over these repeat units, these primitive cells in 3 dimensions, all of them. Before we did a sum over all of them along our 1D line. Now we're doing a sum over all of them in 3 dimensions. Okay, we got, looks to me like we've got 3 minutes left. So the next thing we're going to do, and we'll just do this next time, is for each one of our orbitals on each one of our atoms, construct our block sums. And that's going to be the basis we're going to work in. And then once we have that, we'll go ahead and construct our Hamiltonian matrix elements exactly like you have to do in your homework, but now we're doing them in 3 dimensions. And so when you take the matrix element, you'll be summing over the, now you have 2 nearest neighbors on your line for an A atom. There's a B atom, to the left and the right. Now for an A atom, there's going to be 4 B atoms. And we have to do this. You'll end up doing summing over the 4 nearest neighbors in a 3-dimensional space. But conceptually, it's the same thing. We'll do that next time. And homework's due next time.